In the last video and the videos before that, we saw Euler's formula and how we could rewrite sinusoids into some complex exponentials by only assuming we are looking at the real part. Well, in this video, I'm going to show you that there is another way of rewriting your sinusoids. So if we have our sinusoid, or a sum of sinusoids, denoted by xt, is the sum of a standard coefficient and the sum of how many exponentials or how many sinusoids you have, ak, each with their own amplitude, times the cosine of 2 pi times the frequency of this sinusoid times t plus the phase shift of this specific one. And we have multiple sinusoids now added together. And we can rewrite this as another way, namely, as we have seen in the previous video, where we would rewrite this as a real part of complex exponentials. So we would have k is 1 up until how many sinusoids we have of xk, of the real part of xk, where xk and x0 are also amplitudes, but they also have an e power included in them. That's why they are called x right now and not a, but it's not that important for now. Times e to the power 2 pi times fk times t times I. And now we're going to look at a third method that is mostly used in the rest of the course, chapter and everything. That is that we are rewriting our function with help of the inverse Euler's formula. And this is denoted as a sum from k is minus n up until n of ak, which is a complex amplitude, times e to the power of I 2 pi times fk, the kth frequency, times t. Like I said, this is a complex amplitude. And this is a third way of rewriting a sinusoid. And with this, you can actually make a spectrum representation of your function. Furthermore, this is all denoted with a t, a variable t. You're looking at time. And we can rewrite this in a fashion that we are only looking at frequencies, which can be very helpful because in the end, we are looking at specific filters where we want specific frequencies out. If we record something and we get frequencies higher than 22k hertz, we humans can't hear that. And if we want to record something that is designed to listen to by humans, then we can just throw everything away that has a higher frequency than 22,000 hertz. So how does that work? Well, this is a not so robust way of doing this. This is like a vaguely way of the Fourier analysis, but that will be in another video. For now, we are just going to rewrite a cosine or a sinusoid into its complex exponentials with this third way. And then we will create the spectrum. So let's do that. We have a function, xt. And the function is the following. We have 4 plus 2 cosine 120 pi t plus pi divided by 6 plus 6 cosine 220 pi t minus pi over 3. So these are the sinusoids that we have with a standard amplitude of 4. Now, we want to rewrite this and use the inverse formula of Euler. Recall that the inverse formula of Euler is the following. Cosine of x, this is the formula you should be able to dream, is e to the power ix plus e to the power minus ix divided by 2, but dividing by 2 is the same thing as multiplying with a half. So let's do that for now, because that is easier to write down. So we transform our cosines with this formula. So we get 2 times a half of e to the power 120, so we get I in front of this, 120 pi t plus pi over 6 plus e to the power minus I, 120 pi t plus pi over 6. Like that. And for the next one, 6 times a half of e to the power of I times 220 pi t minus pi divided by 3 plus e to the power minus I of 220 pi t minus pi over 3. Like that. Now we have this. And let's work out the brackets. So we get 4 plus, well, 2 times a half is 1. Then we get e to the power, and let's work out the brackets in the powers as well. And we can split up those powers instantly, which makes it so much easier. So let me color what I'm going to do. I'm going to multiply this I with this pi over 6 and split up the powers. So we get I pi over 6 times e to the power I 120 pi t. This is the same as just having one e and plus between them and working out these brackets here. I just did 2 steps at once. And the other one we can do exactly the same. Here we get e to the power of minus I pi over 6 times e to the power of minus I 120 pi t plus 3 times e, and here we're going to do the same thing. We're going to work out these brackets and we're going to split up the e powers. So we get minus I pi over 3 times e to the power of I 220 pi t plus 3 times e to the power of I pi over 3 times e to the power I 220 pi t minus in front of it. And this one is a minus here, and this one is not a minus, and that is because pi over 3 in itself had a minus in front of it. So these minuses cancel each other out. Now this is good and all. Now what? Well, recall that the standard form of a complex exponential was of the form an amplitude times e to the power I times 2 pi times fk times t. And we want to know the frequency of each of these signals, and we are interested in the complex amplitude. So, for this example, our frequency representation of our lowest frequency. So each of these frequencies we have to split up, meaning 120 pi we have to divide by 2 pi. So we get here, let's write that down in cyan, we get 2 pi times 60 is 120 pi. For this 120 pi is the same thing. We get 2 pi times 60. And for 220 is the same thing as 2 pi times 110. And for this 220 pi, we also get 2 pi times 110. And we're also going to incorporate the minuses. So this minus will be in front of this 60. And this minus will be in front of this 110 as well. So now we have rewritten it in this form over here. We can write down the complex exponentials, and we're going to write them from the lowest frequency to the highest. So our lowest frequency is minus 110. And that is this one here. Actually, let's do that differently. First, we're going to do this one because it's the lowest frequency. It is minus 110, and its amplitude is this. Is what is in front of the e power, which has in its power a t. So in our case, that is 3 times e to the power I pi over 3. Now for the next one. The next lowest one is minus 60. Minus 60. So we're looking at minus 60 and its complex exponential here. So we get minus 60, comma, what we see as a complex amplitude is e to the power minus I pi over 6. Then the next one. Our next frequency is actually a frequency of 0, because if this value is 0, then the whole power is 0, which gives us e to the power 0, which is 1. And that actually is the case if we look at this single value of 4. It actually has a frequency of 0, but it has an amplitude of 4. So we write that down as this 4 will be a frequency of 0 and an amplitude of 4. Now for the other ones, let's go into purple for these. The next frequency is 60 with this as its complex amplitude. We have 60 as its frequency and e to the power I pi divided by 6 as its amplitude. And now the last one in our frequency spectrum representation. Our highest one is 110, and this is our complex amplitude. 110 with a complex amplitude of 3 e to the power minus I pi over 3. And rewriting a sinusoid in these frequency domain is very important later on. Now we can create a spectrum representation of these values. A spectrum representation, also called a two-sided spectrum. We're going to write the frequencies below. So our first frequency is 0, and its amplitude has a length of 4. Then the other ones were minus 60 and 60. These had amplitudes of e to the power minus I pi divided by 6 and e to the power I pi divided by 6. So we're going to write the correct amplitudes at the correct frequencies. So here we get e to the power minus I pi over 6. And here we're going to draw a line with as amplitude e to the power I pi over 6. Then we had one for 110. And the length of these how do you call it, bars or lines, whatever, it's just dependent on the length of the amplitude. And normally we just look at the value in front of it, and this time it's a 3, so I draw it a little bit larger, but there's not really a reference scale. For minus 110, it was 3 e to the power I pi over 3. And here at the right side, we have also 1 at 110, with as an amplitude e to the power minus I pi over 3, which was stated here. Now this is our spectrum representation, and this is how you draw such a spectrum plot. One more important notion is, when we have written everything down in terms of frequencies like this, we can actually calculate the fundamental frequency, or even better, the cyclic fundamental frequency. So our cyclic fundamental frequency what does it say? It says the lowest possible frequency that can be built into these frequencies that we have. In other words, if we take the greatest common divisor of all our frequencies, in our case it's 60 and 110, we will be able to get the biggest frequency possible that these frequencies are built out of. So here we obtain that the greatest common divisor of these two is 10. So we know our cyclic fundamental frequency is 10. So that means this is, of course, the 0th frequency. This is the 6th frequency, and this is the 11th frequency, because we're taking steps per 10, and because this is a frequency of 60 and a step of 10 each time, that means it is the 6th frequency in our spectrum. Of course, we also have the cyclic, not the not the cyclic. We also have the angular. I can't write anymore. The angular fundamental frequency, and this is very easily calculated with just 2 pi times our fundamental frequency, which is actually denoted by f0. And in our case, this is 20 pi. And then, of course, you also have the fundamental period, which is also easily calculated by 1 divided by f0, which is t0, which in our case is 1 over 10. So this is how you calculate these fundamental frequencies. This is how you transform a sinusoid into complex exponentials. And this is how you calculate the frequencies that associate with these sinusoids, and how to plot its spectrum plot. And a spectrum plot represents all the frequencies that a sinusoid has. And once again, it is important to be able to rewrite a sinusoid into this form for later chapters.